In a small telescope, you look at Jupiter, and this is what you see. You see the planet Jupiter. Now, actually, you'd normally see it with stripes on it, and then 4 dots that move around. And so that's Jupiter and its moons. The stripes are washed out in this photo, which is overexposed, and so you just see a big round ball for Jupiter. But this is through a small telescope. That's what Jupiter and its moons look like. And for even large telescopes on Earth, these things are so far away, they really don't look a whole lot more than just dots anyway. And so for the longest time, that's all we knew about the moons of Jupiter. And so we needed to know what they were like. And so our first up-close view of the moons of Jupiter did not come until the 1970s. And that's when we launched spacecraft there. Now, the pioneers were the first to get to Jupiter, but they didn't really investigate the moon so much. They were just experimental, can we get there type spacecraft. The Voyagers were really the ones that gave us our first high-resolution images from the area of Jupiter. And even then, they were much lower technology than what came later. So the Galileo spacecraft, which came decades later, was vastly better. Even though it had a damaged main antenna, it sent back better pictures. So on the left over here is what a Voyager picture looked like. On the right is what the Galileo pictures looked like. Juno is even better than this, of course. And so this gave us the very first views of kind of what the overall structure of the moons is, more detail from Galileo. The outermost of Jupiter's 4 big moons, and we sometimes call these the Galilean moons after Galileo Galilei, because he was the one who popularized and made these things famous. So these 4 big moons are the ones that Galileo saw. The outermost one is Callisto. And so Callisto, when they looked at it, they noticed this is an extremely heavily cratered body. Very large number of craters. That suggests that this surface is very stable. It doesn't undergo much in the way of change. There's no plate tectonics, no volcanism, no motion of any sort, no fault lines, no anything of that sort. So once an impact happens and makes a crater, the crater stays there until something else hits it and covers it up. Now, one of the things they did notice, though, it was kind of odd, there were no really big craters. Now, there were very big marks. For example, here we have this great big mark right here, and sort of concentric sort of rings around it, as if some big shock wave had gone through, cracking the surface. And so that's kind of a hint right there as to what's going on. It's a fairly dark world. It's got dust and debris on it, meteorites, interplanetary dust raining into it. That makes it dark. Wherever there is an impact, though, particularly a fresh impact, it's bright. Those bright spots indicate that the surface is bright underneath. In fact, very bright, reflects enormously, like 90% of the light that hits it. Well, the only thing we know of that's that reflective is ice, suggesting that this is an ice world. It's got a thin layer of regolith or dust and dirt on the surface due to the meteorite impacts, bringing rocky stuff in, but underneath that is ice. Crater chain. This was a huge shock when they discovered this line of craters right there. And for a long time, they had this huge argument over what that line of craters represents. For one thing, it may be a crack or a line of volcanic craters, but that did not seem to make sense on a world that has no volcanic activity. So that suggested maybe that something else was going on. They finally got a clue when they saw the Shoemaker-Levy 9 comet. And remember, when that comet passed by Jupiter, so the comet, we had Jupiter, the comet passed by Jupiter, and it broke into a whole bunch of little fragments before it came back and hit Jupiter, all the little fragments. Well, what would have happened if there had been a moon out here right after it broke into pieces? Then it would have left a line of craters like that. So that suggests maybe something like Shoemaker-Levy 9 had happened before, except it ran into Callisto instead of circling around running into Jupiter. All those craters right there indicates a very old surface. The lack of big craters was a little bit puzzling until they began to realize that this moon is probably a mixture of rock and ice. Remember, we are a long ways from the sun out here, 5 times farther from the sun than Earth is. So at that distance, then water is pretty much perpetually solid, and so it's one of the building blocks. So this thing is about half and half, a little bit more rock, iron than ice. The rocky stuff, would be a little bit more concentrated towards the center, icy stuff a little bit more to the outside, and in that case, that would explain the lack of really big craters, because ice will flow. Think about glaciers. Glaciers are flowing ice, and so that would suggest that maybe ice would flow and would actually cover up some of these craters, or fill in some of the craters. So a big indentation, the ice would relieve itself and the pressure and just squish into that area. The inner part is the rock-iron mixture. Okay, really interesting thing is that Galileo detected and Juno confirmed a very, very thin atmosphere of carbon dioxide. Possibly outgassing from things in here. Now, generally, it's so thin, we'd say this is an airless world, but there's just a tiny, tiny little bit right there, way thinner than, even Mars is at. So the crust, which is very icy, is probably 150 kilometers thick. Inside, most of the moon is probably a mixture of rock and ice, and probably there's a salty ocean. Now, if you squeeze ice enough, you can actually squeeze it into a liquid. This is actually a little bit different than most substances. Most substances, if you squeeze a liquid, you can squeeze it into a solid. Water is weird. Water, if you squeeze ice, you can actually squeeze it into a liquid, because it turns out that liquid water takes up less space than ice does. And so you can squeeze into a liquid, so that would suggest that while it may be sort of an ocean of liquid water, it's only liquid because of the incredible pressure it's under, which means it's not going to be kind of the same kind of environment that you think of when you think water. It is a little bit salty because they realized that it does conduct electricity as Callisto moves through Jupiter's magnetic field. Salt water conducts electricity. So there's believed to be this salty ocean. Now, I say ocean, I really probably should say salty layer. Most books call it ocean, though, which is why I use that term. But it is nothing like what you think of when you think ocean. The next moon in is Ganymede. So this is the third out from Jupiter. And so Ganymede is the next of the Galilean moons. Ganymede is interesting because it has craters, but it also has dark and light splotches on it. Ganymede's the biggest moon in the solar system. A lot of old books used to say that Titan, one of the moons of Saturn, was the biggest in the solar system, and that's because Titan has an atmosphere and a layer of clouds. And so they did not really know how big Titan was, so they just measured from one side of the clouds to the other. The clouds turned out to be very high in the atmosphere, and so once they were able to measure the size of the moon itself, they realized that the solid part of it is actually smaller than Ganymede by a little bit. Ganymede and Titan are both almost the same size, just Ganymede's a tiny bit bigger. Between Mars and Mercury in size. And it is one of the ones visible in binoculars because it is so big. Callisto's almost as big, and so Callisto is just barely smaller than Mercury, and so Callisto is also sometimes visible in binoculars. Looking at some of these dark splotches on Mercury, we realize that it's got wrinkle ridges in it. Well, wrinkle ridges, that's kind of weird. We have kind of wrinkly surface material. If you look in this gap in between, we have cracks and fissures. Well, that's kind of like what you would get if you were like pulling apart something, almost like rifting. Wait, wrinkling and rifting, squeezing and pulling apart. What does that sound like? That sounds like plate tectonics. Ganymede is showing evidence of something similar to plate tectonics. Now, it's not quite the same because we believe that the outer part, like on Callisto, is icy. So these would be like giant icy continents and then ocean type stuff with ice volcanoes coming up in between in the rift zones. So this is like icy plate tectonics. So that makes it quite a bit different. The ancient terrain with craters, the younger terrain with grooves. The ancient terrain would be like the continents. The younger terrain, that's going to be like the oceanic ridges right there. And so this, again, this suggests structures and features that we normally think of as plate tectonics. Now that's important because we've never seen plate tectonics on anything other than Earth except for Ganymede. And so this is not exactly how Earth's plate tectonics works, but it's close enough to give us an idea as to what's going on and how to study Earth by studying Ganymede. So the crust is this icy layer that's floating on a slushy, watery mantle. So that means it's able to flow. There's a differentiated core with iron, nickel, we think, in the middle, and a rocky shell around the outside, and this icy, slushy sort of thing, this mantle that's able to flow like the asthenosphere on Earth. It does seem to have a weak magnetic field of its own, again, suggesting it has a partially molten core.